All right, so we are going to start a fresh video here with section 4.3, homogeneous linear systems. So this is going to look, like we've solved homogeneous before. So there are going to be parts of this that look similar, and then there's going to be parts from our matrix learning that we're going to bring in to further our understanding of how to deal with these linear systems. So we're doing some defining today. And we will do some more examples and practice with it tomorrow. So to define our first order linear system, again, remember this is what the standard form looks like right here. Now we are adding on to this that if g of t is equal to 0, we consider the system to be homogeneous. So remember again, when you are defining your matrices, g of t would be all of those constants on the other side, on the right-hand side of our equation. And we typically know that to be the case, that if the right-hand side of our differential equation is equal to 0, we call it homogeneous. That will be the same as long as that's consistent for every single one of our differential equations in the system. So basically what we end up having is y prime is equal to p of t times y. That's our system where we can apply, again, the principle of superposition. If you remember this, that initially what this states is that y of t is a solution where we can take and add c1 times y1 plus c2 times y2 if y1 and y2 are solutions, that by adding them, we get another solution. Well, notice how we've just added to this vector notation. So y1 would be a vector valued function where y sub 1 is a solution that is represented by some type of matrix here that gives you your solutions. Y2, the same, okay? So we're saying that, again, we can multiply some constant C1 and some other constant C2 and add these all together, and we get a full general solution as long as any Y1, Y2, and so on up to Y sub n that we're discussing form a fundamental set of solutions. So we talked about fundamental set of solutions before. We're going to continue talking about them here. Where we talked about this before was when we started talking about matrices. And so we're going to go ahead and do an example here where we have y prime is equal to a times y, where a is our coefficient matrix that looks like this. Now, what we want to do is we want to verify that we do actually have some solutions here, and we're going to verify using substitution, which is a method that we've used before. And so we're going to use that again. And I will give you y2 and y3 down here to try on your own. We're going to go ahead and do y sub 1 together. So basically, since we just have a first order right here, we only need to concern ourselves with first finding y1 prime. All right, so in order to do that, like we discussed in section 4.1, we are just finding the derivative of each respective element. So that would be 2e to the 2t, 4e to the 2t, and still 0. Okay, so by substitution, now we're saying we should be able to take y1 prime and y1, plug them back into our differential equation here with a, and make sure that this does in fact give us a solution. So y1 prime right here, y1 prime is equal to a times our vector value function y. So a is this. And we are going to multiply that by what we got specifically here for y1. So all right, so little matrix multiplication here. And when we do that on the right-hand side here, So I'm going to go ahead and write out what we get for each of these. We get 0 times e to the 2t plus 1 times 2e to the 2t would just be 2e to the 2t, and then plus 0 for this first element in the first row. Then it looks like we get negative 6e to the 2t plus 10 e to the 2t by multiplying 5 here by 2e to the 2t plus 0. And then we get 0 e to the 2t, 0 times 2e to the 2t. So just 0 again, and then another 0. So if I go ahead and simplify, then it looks like I am getting 2e to the 2t for my first element. I get 4e to the 2t where I combine like terms there, and then my last element is just 0. So this does in fact check out. Y1 prime right here matches with my right-hand side when I multiplied that out. So now I want you to go ahead and try Y2 and Y3, and go ahead and pause the video here and give that a try, and I'll meet you back in a second. Okay. Even though you had to watch me fumble around to try and pause the video, figured I'd spare you having to see me write this stuff in. So hopefully this is what you got. Here's what I got for Y2 prime. I did my matrix multiplication and I kind of simplified this down a little bit, but this does check out that this is Y2 prime right here. Same with Y3 prime. The derivative there is pretty straightforward and does in fact match with the matrix multiplication that we do on the right-hand side. Okay. So this is part 1 of showing a fundamental system or fundamental set of solutions. Sorry. Part 1, okay, of showing that. Part 2, if you remember with matrices, maybe you know what part 2 looks like here, but it is the Wronskian. Okay. Now, we won't always use substitution. You've seen in the past where we kind of start with substitution and then we move into other, easier, faster methods, more efficient methods. So the Wronskian determinant is definitely that. So if we are looking to prove that we have a fundamental set of solutions, we can do this in matrix form because we've learned the Wronskian. We use psi, this Greek letter psi, to represent the Wronskian determinant. Kind of looks like a W. So we call this a matrix, specifically psi of t, where as long as this is basically our solution matrix, but more specifically, this is our fundamental solution matrix. So once we have, proven, or if we want to prove that we have a fundamental set of solutions, we get it into this fundamental solution matrix psi of t, where, instead of each of these being separate vector value functions, we put them all together as 3 columns in this matrix. So in order to find the Wronskian, we have to do the determinant of a 3x3. So that determinant, remember, is going to look a lot like doing our cross product here. So if we want to do that, let me just go ahead. No, we'll do it in this color. That's fine. So if we want to do that, the Wronskian is going to look like e to the 2t. We start, by going across the elements in the first row here. E to the 2t is going to get multiplied by this 2x2 determinant right here. Multiplying 3e to the 3t by e to the t gives me 3e to the 4t minus 0. And then don't forget to change the sign on the middle. I won't talk you through the rest of this because you remember. The last one here, we're going to get 0 times whatever. It doesn't matter. It's just going to be 0. So now remember that the whole purpose of finding the Wronskian is we want to verify that the Wronskian or our determinant is not itself equal to 0. We are just trying to prove that it is something other than 0. So if I go ahead and multiply here, I get e to the 6t, I'm sorry, 3e to the 6t. And then here, I'm going to get minus 2e to the 6t. So this answer itself is e to the 6t, which is not equal to 0, which does mean that, yes, this is good. And we would say that listing out y1, y2, y3 as their individual vector value functions form a fundamental set of solutions. We already knew that from the work that we did with substitution. So like I said, this altogether is just a quicker, less clunky way of proving that you do have a fundamental set of solutions. Okay, so y1, y2, y3 form this fundamental set, and the general solution then would look like y of t is equal to, we take our C1 times Y1 plus C2 times Y2 plus C3 times Y3. This looks the same as we're used to, but now each of these Y1, Y2, Y3 are vector value functions. Okay, so the way we write this out is that Y is equal to psi, our solution matrix, times C, our constant matrix, those C values that we add in. Now, if we're doing an initial value problem, we obviously solve for C. For this one, we are just going to go ahead and write it out. So let me pull up here so I don't have to keep scrolling. Okay. So psi of t looks like this. Remember that this was y1, y2, y3. Okay, so that's just pulling down psi of t. And then we're going to take that, we're going to go ahead and multiply it by my C matrix. So that's just going to be C sub 1, C sub 2, C sub 3, and that's how we'd represent it. Now, again, if we are solving for C1, C2, C3, then we would probably be using some of our matrix operations that we know and I am sure love from our previous unit. So this one, obviously, we're not worried about that. Okay, so those are, those are kind of the basics. We did go through some examples while defining that a little bit, and we will do more practice with that tomorrow. So I hope you have a wonderful day, and try the homework and let me know how it goes, and I will talk to you later.